Cord to the cloud. Right, so yesterday we talked about, ended with the combined gas law, just talking about all of these together. We also went over Boyle's law, which is a combination of, or is the relationship between pressure and volume. We talked about Charles' law, which is the relationship between volume and temperature. And we talk about Gay-Lussac's law, which is the relationship between pressure and temperature. So combining all of these three things together gives us a more powerful equation where we can work with multiple variables at the same time, multiple changing variables. So we did this problem where we had our ammonia gas, and we'll move on to this one. So again, the steps when you're going through a problem like this, you read through it once and then write down all of the numbers that it's giving you and line them up with the variables. So to what temperature, we want this in Celsius, so that's important, so let's highlight that. To what temperature must 10 liters of nitrogen at 25 degrees C and 700 torr be heated in order to have a volume of 15.0 liters and a pressure of 760 torr? So we're gonna have, well, actually, first we're gonna have temperature, right? Because it's asking us for temperature. And this is one of those questions where it's saying it can be tricky, the order that they give you these things in, because it says to what temperature. So we know that we're going to end up at some end temperature. So this is actually going to be our T2. So to what temperature must 10 liters? It'll be V1. And then we'll have our T1 as we have nitrogen at 25 degrees C. And oops, pressure here. P1, 700 torr. In order to have a volume of 15 liters and a pressure of 760 torr. So our V2 then is going to be 15 liters. Pressure P2 is going to be 760. Figure out what's going on with my Apple Pencil. 760 torr. All right. Now, based on this, we could go back and we could look at all of the equations that we have, or we can just use the combined gas law. And we know here that it's going to be the combined gas law because we have volume, temperature, and pressure, initial and ending values. And we have a change in both volume and a change in pressure. So now at this point, we can just plug these in. Oh, sorry. Before we plug these in, we need to change our temperature here to Kelvin. So just add 273.15. Let's grab my calculator. So we're going to do 25 plus 273.15. That is going to be 298.15 Kelvin. So now that we have that, we can start plugging some things in. So P1, V1 over T1 is equal to P2, V2 over T2. Sorry, I forgot the one there. Actually, in all likelihood, my pencil didn't write it down. So we've got 700 torr. V1 is going to be 10.0 liters. Or T1 is going to be 298.15 Kelvin. And then we'll plug in these numbers over here. So we're going to 760, which should be recognizable as the standard pressure, right? 1 atmosphere is 760 torr. We're going to have 15 liters. And divided by T2. So that's going to be our unknown. So I'd start here by doing all of this math on this side. We'll do 700 times 10. and then divide by 298.15. So that'll give us 23.478. Again, more numbers after that. And our units here are going to be torr liters per Kelvin. And then on the right side, I'm going to go ahead and do this as well. We're going to do 760 times 15. A lot of these problems come down to algebra, so if you're struggling with the algebra, you might want to find a Khan Academy video, brush up on that. And then that's going to be over T2. So now to move, we want T2 to be in the numerator. Otherwise, we're going to get 1 over T2. So we're going to multiply both sides by T2. We're going to multiply this side by T2. And then we're also going to divide by 23.478 on both sides. Torr liter Kelvin. Because after we do that, all right, this will be canceled out because we're dividing by itself. And this will be canceled out because, again, dividing by itself. So the final math that we end up doing here is going to be 11,400 divided by 23.478115, a bunch of numbers though. So temperature 2 is going to be 485 56 Kelvin, but we're not quite done yet because this is asked for degrees Celsius. Well, somebody on Zoom is not muted. There we go. All right. So we have to convert this back to degrees Celsius because that's what our prompt has asked us for. So to get degrees Celsius, we take our 485.56 minus 273.15. And so our final answer will be, it's a really big number. And temperature is going to be 212. I mean, at most we have kind of 3 sig figs. 212 degrees Celsius, which is real hot.
I think it's the number P2, is that 760?
Yeah. What are you doing back there? There's all this free real estate. Yeah, and then I'll post these slides afterwards with the notes on them, as well as the video from yesterday and today's video. So our mole mass volume relationship, the mole mass volume relationship of gases. This is a very, very useful relationship. So because a mole contains 6.022 times 10 to the 23 molecules, or atoms, or things, a mole of any gas will have the same volume as a mole of any other gas at the same temperature and pressure. So we go back to the kinetic molecular theory. Pressure and temperature, temperature kind of. Pressure and volume are all kind of related to the number of moles that are in a space or in a volume. And for other things, the density is determined by how closely they pack, but because we're assuming that all gases are infinitely spaced apart, sort of relatively speaking, they're all going to take up the same volume. So a mole of any gas is 22.4 liters at STP. So that will change if you change the temperature, and it'll change if you change the pressure. But if you're given a question and it says at STP, so a question could be, erase please. How many moles of oxygen are in 22.4 liters at STP? And that would be 1 mole. And if it was oxygen, nitrogen, methane, if it's cyanide gas, it's all 22.4 moles, or 22.4 liters is 1 mole. So if you want to write that out as like a straight up conversion factor, 22.4 liters equals 1 mole. So yeah, molar volume is super useful for determining the molar mass of a gas, because if the mass and the volume of gas, or we have the mass and the volume of gas at STP, we can calculate its molar mass. So if we have 2 liters of a gas, 2 liters of a gas measured at STP, that's critical. STP has a mass of 3.23 grams. What is the molar mass of the gas? So just to recap, molar mass is in units of grams per mole. So we don't even need an equation here. If you can remember what the units of some of these things are, you can usually calculate them, unless there's a constant involved. And we'll get to the constants. Well, one example of a constant would be heat capacity that we covered already. There's also the ideal gas law constant. So if we have 2.00 liters of gas at STP, we know that 1 mole is equal to 22.4 liters. And so we can do this math, cancel those out and get moles. So it'll be 2 divided by 22.4. So our number of moles of this gas is going to be 0.089 to a bunch of numbers, moles.
So the 2.24 is kind of like the 6.022 times 10 to the 23rd power. It's like it's a same number.
It's well, 6.022 is like how we've defined 1,000, right, as 1,000, or like a gross is 144 things. So mole is the way we count things quickly, or like dozen, right? We've defined it as this number, so we can say I've got 4 dozen eggs, and that's easier to say than I have 48 eggs, or it's easier to write more specifically, especially when you get up to bigger and bigger numbers. 22.4 liters is a convenient conversion factor at STP. One of the few that you get. So based on this, we have this many moles, and we know the mass of the gas. So we can calculate this molar mass. To do that, we can just take our 3.23 grams and divide it by 0.08928 moles. So 3.23. So molar mass of this gas is going to be 36.17. Well, I guess sig figs here, huh? 36.2 grams per mole. I figure out what that would be. Because it could be an isotope of chlorine. No, because chlorine would be Cl2. Sometimes you can use the molar mass to figure out what just the identity of something, especially if it's a small enough molar mass. It limits the number of possibilities that you could have. All right. Moving on though. So measured at 40 degrees C, 630 torr, the mass of a 691 milliliter diethyl ether is 1.65 grams. Calculate the mass, the molar mass of diethyl ether. So how do we want to attack this problem? Let's write down all the stuff that we have first. So we've got a temperature, that's 40 degrees C. We've got a pressure. We don't know if these are going to be 630 torr. And then we've got a volume, 691 milliliters. And we have a mass as well, 1.65 grams. What equation do you think we're going to use for this? Where's this going to fit in?
Wouldn't we do what we just did on the other one? Or not, we wouldn't do it because we don't have STP. We wouldn't do the gram.
Right. It's a good try. Good try though. Yeah, I mean, okay, we just did a problem. That's a great way to think about it. We just did a problem where we did this thing. Knowing though what we know, so we have this equation, right? P1, B1 equals, or over T1 equals P2, P2 over T2. So what if we want to know the volume at STP, right? Because if we know the volume at STP, then we can use our 22.4 moles per, or liters per mole, and then get the moles.
So how do we find STP?
Well, let's assume that we just take this gas and we change it so it is at STP. Because if we do that, so if we take this, just try to give myself more room. Well, first let's do this, right? 273.15. Can't be working in degrees C. They're peasant units. So 313.15 Kelvin. So I guess we should say first, let's call these our T1, P1, V1. What is STP?
Secondary ones.
What is the temperature at STP? So STP stands for standard temperature and pressure. So our standard temperature is actually 273.15 Kelvin. And our standard pressure is 1 atmosphere. But 1 atmosphere would be a little harder to work with here because we've been given a unit of torr. But one of the units that's helpful to memorize at the very least is that 760 torr is equal to 1 atmosphere. So instead of using atmospheres, we can write, we're going to change this to 760 torr. And then this final volume, this V2, is then what we're going to be looking for. So the incredibly powerful thing about this equation is that we can take any gas, as long as we know its temperature, pressure, and volume under one set of conditions, we can say, oh, well, we'll just change pressure and temperature to the ideal conditions and then determine things based on that. Or we could set it to anything else we want to do too. We could calculate for this room, like we could get that atmospheric pressure, we could calculate the volume of this room, and we get the temperature of this room. And we could say, well, what would happen if we heated this room to 1,000 degrees Kelvin? How big would the air, like what would the volume of the air be after that? Or what would it be at STP? And then we calculate how many moles of air are in here. And later we'll be able to calculate how much oxygen is in the room. These are the kinds of things that I think about when I'm writing questions. So this will go, there will probably, I'll say it right now, there's probably going to be a question on the next exam. This will be like the hard question. That will be, how long could you last in this room if you're the only person and it was sealed tight? And then I'll give you a bunch of parameters and stuff and calculate the amount of oxygen that's in the room. And then I'll give you like the breathing rate, respiration rate of a single person. Anyways. To get back to this though, let's convert this into STP. So we're just going to plug in our pressure. And I'm sure while I was ranting, some people were already working on that. We're going to have 691 mils, which I'll highlight this because it's important to remember that it's in milliliters and not liters. We can convert it now or we can convert it later. We'll convert it later. So over 313.15 Kelvin. And then our pressure, these are going to be standard temperature and pressure, 760 torr. Our volume is what we're looking for. And then our T2 down here is going to be 273.15 Kelvin. All right, STP is, I always forget what STP is. Let me just double check this real quick. Does somebody have it in their notes faster than I can look it up? Standard temperature, I'm pretty sure, is 273. Yeah. Okay, good. Because there's a lot of measurements in chemistry that are done at 25 degrees Celsius. And the reason 25 degrees Celsius is used is because it's slightly warmer than room temperature. And it's a lot easier to heat things up in a lab than it is to cool them down. Okay, so we can solve this left side easily enough. 630 times 691 divided by 313.15. And that will give us 1,390.16. And then on the right side, I'm going to do 760 divided by 273.15. This will be 2.78. What I'll write down. Again, when I write these numbers down, I'm going to use the entire number that's saved in my calculator. So we're going to do this 1390.16 divided by 2.78. And we're going to get right around, that's fun. Let's just, we're going to get 499.64 milliliters as our V2. Now our molar volume at STP is in liters. So we need to convert our milliliters to liters. We can do that by dividing by 1,000. So we're going to get 0.499, oops, not another decimal, 64 liters equals V2. And then didn't leave myself much room. So 0.49964 liters times 1 mole, because now we're at STP, is 22.4 liters. So liters can cancel to give us moles. So divide this by 1,000, whoops. Divide by 22.4. So still not quite done yet, but 0.0223 moles. And so now our molar mass is going to be grams divided by moles. And again, I'm just not leaving myself much room. It does a long problem. I can shrink this. Squish it over there. Okay, so we're going to take our moles here. We're going to do 1.65 grams per 0.0223 moles. So we're going to get 73.97 grams per mole. And if we want to check our answer real quick, diethyl ether is C4 for C4 H10O2. So this is we've calculated now using, for this gas, we've calculated using temperature, pressure, volume, the molar mass. So if this question was written correctly, we should be able to also look at the molecular formula for diethyl ether and calculate its molar mass using the periodic table. So carbon is 12.01, hydrogen's 1.01, and oxygen is 16. Also, if I wrote down the correct formula. So 12 times 4 plus 12.01 times 4, and then 1.01 times 10 plus 16 times 2. Oh, wait, no, it's not O2. Okay, good. That was wrong. Okay, so there's only one. So, right, so we multiply this by 4, multiply this by 10, multiply this by 1, and then we add those all together, and we get 74.14. And that is more than close enough. You always have to account for a little bit of experimental error. There's probably some error. If this was a real experiment, there would be error in this volume, a little bit of error there, a little bit of error in the temperature, a little bit of error probably in the volume as well, and the mass. So you have to take all of those things into account. So to get a value of 74.14 compared to our calculated 73.97 is pretty good. And actually, I'm going to go ahead and pull back another concept that we've covered before, or should have covered before. We can calculate our percent error because we know our value from the periodic table. We know our experimental value. So the theoretical value of 74.14 minus 73.97. So that's our calculated or experimental divided by 74.14. And then we'll multiply that by 100, and that will give us our percent error. So our percent error then is 0.2%, which is really good. So I talked about yesterday, these things all sort of build into these individual stacks of concepts. And a lot of these build on each other, but there is interrelationship between all of them. So if you're told that you have diethyl ether, you can calculate a molar mass this way. You can also calculate the molar mass based on the values that you're given.
So which would be easier?
This would be easier, much easier. So on a question like this, though, I would be looking for some sort of work to show that you did this. And I would probably ask you, I would probably, play with these numbers, right? And get it so it was a little bit off like this. So then when you do the question, if you get this answer, then I know you just used the periodic table. But if you use this answer, then I know you did it the way I was expecting you to. Okay. That was a deep dive. Yes, moles. So we've got pressure and volume, Boyle's law. We've got volume temperature, Charles' law. We've got Gay-Lussac's law, which is pressure and temperature. And now we've got volume and moles. This is the first time that we're actually looking at the relationship between moles and our other values. Avogadro, so 6.022 times 10 to the 23, that's Avogadro's number. He also did this work between volume and moles. As I said, the volume of a gas is directly related to the number of moles of a gas when temperature and pressure do not change. So I think I was highlighting these in red. So temperature, pressure do not change. Volume and number of moles are changing here. So this is the thing you experience every time you blow up a balloon. The temperature and the pressure don't change because when you blow into the balloon, you're adding moles of gas and the balloon expands. And that's so adding gas, balloon expands. The balloon expands because it doesn't want to have a higher pressure inside the balloon than outside the balloon. So it automatically matches that pressure. So when measured at the same temperature and pressure, ratios, the volumes of reacting gases. When measured at the same temperature and pressure, the ratios of the volumes of reacting gases are small whole numbers. All right, that's a lot to digest. So for example, hydrogen and oxygen combine to form water in a volume ratio of 2:1. So here we have, why is it 2:1? Volumes here react 2:1 at the same temp and pressure. I would expect this to be 3:2 because we have 2 moles of hydrogen, 1 mole of oxygen forming 2 moles of water vapor. So if you think about this, I'm going to question the slide. All right, so Avogadro's law, and actually we can write it out as, how is it written out? I think it's, right, so N over V is equal to N over V. It's probably actually written the other way, sorry. Erase please. Volume 1 over N1 equals volume 2 over N2. So the volume of gas is directly related to the number of moles of gas. So in this reaction, we have 2 moles of hydrogen. I'll write it out like this: reactants and products. Right. So we have 2 moles of H2, 1 mole of O2, and those form 2 moles of H2O. So our number of moles on our left side is more than the number of moles on the right side. So what happens to our volume? Our number of moles goes down.
Volume will be the same.
Volume does the same. Yeah, they're directly proportional. So if we react to these two things, then our volume is going to decrease. So if you did this like in a balloon, without popping the balloon somehow, the size of the balloon would get smaller as you reacted all of your oxygen and hydrogen. Don't know, this is 2:1. So then the ratio here should be, if I'm not mistaken, 3:2. Yeah. The simple but significant and far-reaching generalization concerning gases, which is Avogadro's law, is equal volumes of different gases at the same temperature contain the same number of molecules, which this ties back to our 22.4 liters per mole, right? So the same number of molecules makes up the same volume. So this offered a rational explanation of Gay-Lussac's law, combining volumes of gases, and indicated the diatomic nature of such elemental gases as hydrogen, chlorine, and oxygen. So if you took those and you put them into a gas, they'd be is heavier than you expected, or would be not as voluminous as expected. It provided a method for determining the molar masses of gases. That's fun to say. And for comparing the densities of gases of known molar masses, of known molar mass. It also afforded a firm foundation for the development of the kinetic molecular theory, right? Where everything is dependent on the number of particles, the size of the box, how fast they're moving. All of these things come out of that kinetic molecular theory. How deep do I want to go into these? Right, so we did this earlier, where we had the volume of a gas and we had the mass of the gas. We can calculate its molar mass. Otherwise, how do you get the molar mass of a gas? So for example, by Avogadro's law, equal volumes of hydrogen and chlorine at the same temperature and pressure contain the same number of molecules. On a volume basis, hydrogen and chlorine react. So 1 volume of hydrogen plus 1 volume of chlorine gives you 2 volumes of hydrogen chloride. Hydrogen molecules react with chlorine molecules in a 1-to-1 ratio. Oh, I see what this is saying. It's talking about the 2-to-1 ratio is between hydrogen and oxygen. I see. Okay. So then assume we have 1 molecule of hydrogen, 1 molecule of chlorine must produce 2 molecules of hydrogen chloride. Therefore, each hydrogen molecule and each chlorine molecule must consist of 2 atoms. Ah, yes. So if we take this one, so if these reacted and it was just 1 hydrogen, right? So hydrogen existed as a gas, right? And it's just a single hydrogen. And we add to that a single chlorine, we would expect then our volume, we would expect then to make a single HCl. So we've gone from a volume of, right, 1 mole, or 1 molecule, and we've gone to 1 mole on this side. So the combined volume here should be based on 2 moles of gas. So our size should decrease because we've gone from 2 moles of gas to a single mole of gas. But what actually happens is we don't have just a single hydrogen and a single chlorine. We have H2 and we have Cl2. So when 1 hydrogen molecule combines with a single or with a chlorine molecule, we end up with 2 hydrogen chloride molecules. And so our volume on this side is actually 2 moles. So if you do this reaction, the volume doesn't change. Because the volume doesn't change, we know that hydrogen and chlorine must both be diatomic to be able to produce 2 moles of gas. Maintain the same volume. So the coefficients of the balanced equation for the reaction give the correct ratios. The correct ratios for the volumes, molecules, and moles of reactants and products. So we end up with our reactants, is 2 moles, and our products. That's 2 moles. So you don't see a change in volume. So this is an example of an experiment where if you didn't know that hydrogen and chlorine were both diatomic, and you went and did this experiment, you'd be expecting, if you knew Avogadro's law, you'd expect the volume to decrease. And then if you didn't see that, now all of a sudden you got to go back to the drawing board and figure out, well, why did the volume increase? And repeat your experiment to make sure you didn't make any mistakes. So the volume of a gas depends on the temperature, pressure, and the number of gas molecules. Different gases at the same temperature have the same average kinetic energy. Lighter molecules travel faster and heavier molecules travel slower, but both have the same average kinetic energy. So something like hydrogen, right, H2, has a mass of 2.02 grams per mole. But something like chlorine, CO2, is going to have a mass of 70.9 grams per mole. So for these to be the same temperature, hydrogen has to be moving, 35 times faster than chlorine. Because our mass or kinetic energy is this equation. It's mass times volume as volume squared, or sorry, mass times velocity squared. So we have two gases. The two gases are at the same temperature and occupy equal volume and exhibit equal pressures. Each gas must contain the same number of molecules. So just reinforcing here Avogadro's law. So now with all of these different laws, we can put them together into the ideal gas law, the one law to rule them all. We can combine these into a single gas equation with the four variables that characterize any gas. You have volume, pressure, absolute temperature, right, kelvins, and then number of molecules of moles. Or number of molecules in moles. We combine these variables. I think what he's getting at, what would he write here? Oh, maybe it's volume is proportional to number of moles times temperature. It's this one rearranged. So this would be like that. We have N, T, and we'd have this value of R over P. R is a constant. This is the ideal gas law constant. And primarily, we're going to be using R as 0.08821. And that's in units of atmospheres, liters per mole Kelvin. So the easier one to memorize is this one, yeah. PV equals nRT.
Wait, so was that 0.0821 is all?
Yeah.
And is that like always, or
As long as you're using units of atmosphere liters per mole Kelvin, it's this.
okay.
Yeah, the units on this are very important because if you're not using those units, you can't use torr, you can't use millimeters or inches of mercury. You can actually recalculate this, right? You can convert just atmospheres into those other units to get the other ones, but I find it's easiest to just use this. So I guess the ideal, ideal gas constant for R for 1 mole of gas at STP. So we can, like I said, it's in units of atmospheres, liters per mole Kelvin. So using those units, and let's write these out over here too. So right, STP, our temperature is going to be 273.15 Kelvin. Pressure is going to be 1 atmosphere. And N is going to be 1 mole. And 1 mole of gas, this is the key, 1 mole of gas at STP has a volume of 22.4 liters. So we end up with 1 atmosphere times 22.4 liters divided by 1 mole times 273.15. So if you don't remember R, but you remember the units, you can calculate R. So if we do this, I'm going to do 1 times 22.4. Actually, don't need to do that, but I'm doing it anyway. So we could divide by 1, or 1 mole times 273.15 is going to be 273.15. So now divide by 273.15. And we'll get the whole number here now, right? So all of the digits, 0.08. Oh, sorry, I was wrong. Make sure you change this. It's 0.08201. Because I'll write out more digits here, right? 6, 2, 2, 4. So I should have said 0.08201. So then you could also do this for, just to show you, right? If we wanted to change the units of R, because we want to use some different units of pressure. It's really the only thing that we're going to use different units for. We could say 760 torr, for example, times 22.4 divided by still 1 mole and 273.15 Kelvin. So this is still STP, just a different unit of pressure. So solving this. So this value of R would be 62.32 in torr liters per mole Kelvin. So you can always calculate R at STP based on the units that you want to use. And yeah, actually, let me do this too, right? So if we use our PV equals nRT equation, R is just what we get when we solve this equation for R. So we'll get PV over NT equals R. So pressure, volume, moles, Kelvin. And then you just do it at STP. All right, so what pressure will be exerted? Pressure will be exerted by 0.400 moles. This is N. Gas in a volume of 5 liters. In a container at 17 degrees C. So 273 to that right off the bat. Get that in Kelvin. So again, like I was saying before, or like I've said multiple times now, you can write down all these variables and then use that to figure out which equation you're going to want to use from there. A key that you're going to want to use, the ideal gas law equation that we got the units for here, is that we don't have an initial condition and an end condition. So we're not changing from one thing to another. We just want to know the pressure of this random gas under these conditions. So then we're going to be using our R value of 0.08201 atmosphere liter per mole Kelvin. So before we even write anything out, what are our units of pressure going to be?
Atmospheres?
Yes, because the value of the pressure value that we have in our R value is in atmospheres. So our equation will be PV equals nRT. So pressure is what we're looking for. Or volume, all right, so multiplied by 5.00 liters. N is 0.400 moles times our R value, 0.08201. That's small, but that's just atmosphere liter per mole Kelvin times our temperature, run out of space. Hey. 290. So first step, we'll solve for the right side of this equation. Let's do 0.4 times 0.08201 times 290.15. Put 9.518. And so we still have 5 liters. And then a pressure. So now our units here have changed on the right side because we took moles, multiplied it by this 1 over moles in these units. So these will cancel. And we took our Kelvin, so that cancels. So now our units that are remaining are atmosphere liters. So when we divide both sides by 5.00 liters, we're going to get P is equal to 1.90, oops, not liters, atmospheres, because now liters cancels. This is why it's important to write out the units that you're using throughout, because when you get to the end, your units should work out. If they don't, it means you missed something. Or use the wrong unit somewhere. Turn the brightness down. iPad's so hot, it's making my hands sweaty. All right, good there? Anybody ask questions in the chat over here? Because I'm not watching it. Oh, yeah, that was a while ago. I had the wrong number for, yeah, that was a mistake on my part. How many moles of oxygen gas are in a 50-liter tank? 22, that's supposed to be degrees C. If the pressure gauge reads 2,000 pounds per inch squared, or PSI. Oh boy, we get to do some more conversions. So how many moles, right? So we're looking for moles, are in a 50-liter tank. Volume equals 50, 100 liters at a temperature 22 degrees C. If the pressure gauge reads, the pressure is 2,000 pounds per inch squared. So again, I mean, context clues, right? Previous slide was ideal gas law equation. This is the ideal gas law equation. Also, again, we're given a static set of conditions. We're not looking at a change. So that's the limitation of the other gas laws, is they can only tell you what happens after a change. They can't tell you anything about a single static condition. You have to know something about it already. the ideal gas law lets us look at those static conditions. Okay, so we're going to convert PSI into atmospheres. We'll multiply by 1 over, so 1 atmosphere, or 14.7 pounds per inch squared. And then we're going to convert our temperature as well, 73.15, which will give us 295.15. Wow. Kelvin. And this will be 2000 divided by 14.7, 136.05 atmospheres. And then a reason we're converting to atmospheres is because I want to use 0.08201 atmospheres, liters, mole, Kelvin. Okay. PV and RT. If you are comfortable with the algebra, you can always solve this for what you're looking for ahead of time. All right, we don't need to plug the numbers into it like this. We can rearrange this because we can treat these variables. Well, we can treat them like variables. So we want to solve for n. So we can divide both sides by RT. And that'll move the RT over to the other side. So we'll get PV over RT equals n. Now it'll be, I don't know, it's really the same number of steps. It's just doing one of them beforehand. So changing the order. So we're going to get 136.05 atmospheres and 50.0 liters over 0.08201 atmospheres, liters, mole, Kelvin, times our temperature of 295.15. Okay. So 136 times 50 divided by 0.08201 divided by 295.15. So we're going to get 281, 3 sig figs, 281 moles of gas. It's going to be N, or moles of oxygen. It's a lot of moles of oxygen, but it's a big tank under a lot of pressure. So that makes sense. Any questions there? Make sure I come over here and check the chat from time to time. Cool. Ooh, calculate the molar mass of butane gas if 3.69 grams occupies 1.53 liters, 20 degrees C in 1 atmosphere. So, right, what we know about molar mass is that it's grams per mole. And then if we write down the other numbers that we're given here, we want to know the molar mass. We're given a gram, so we can write down our mass. Mass is 3.69 grams. And we have a volume, 1.53 liters. We have a temperature, 20 degrees C, and we have a pressure of 1 atmosphere.
This when we change it to STP, right?
Well, I was going to say, there's actually 2 ways we can solve this. We can use, like you're saying, which is great, awesome, love it. We could do PV over T, convert this to STP, and then use 22.4 liters to get the number of moles, which is fine, and that will work. But we can also use PV equals nRT, because we have pressure, we have volume, and we have temperature, and R is a constant. And we're using atmosphere, so we can use R 1. So for this kind of question, it kind of depends on what you feel most comfortable with. But just a quick rearrange here, PV over RT equals N. So same algebra function we did there before in the problem before. And then we'll do, oh, sorry, convert this. So pressure is 1, volume is 1.53, divide by 0.0801. And then temperature 293.15. Ooh. It's hurt. So 1.53 divided by 0.08201 divided by 293.15 will give us 0.06364 moles equals N. And then we can do 3.69 divided by what we got for our number of moles. So our molar mass, I'll just write this in here. Whoops, 6364 moles, and this is going to equal 57.98 grams per mole. No, I didn't feel anything. Right, so let's just try this. What's the molar mass of butane? Asking Siri. 58.078. All right, and so we could again calculate, I'm not going to do it, but we could calculate a percent error here to see how close this calculation was to the actual value. Yeah, it's very close again. But probably, yeah, like 0.2%. So yeah, don't forget that 1 mole is 22.4 liters at STP. We can use we can solve these stoichiometric problems by using this STP and just the mole ratios that we went through in chapter 9. So for a problem like this, what volume of oxygen can be formed from 0.5 moles of potassium chlorate? I love how these slides just did not translate. Okay, so we have, these are supposed to be arrows probably. Cool. So yeah, we want to go from moles of potassium chlorate, 0.5 moles KClO3. And we're going to convert that into moles of oxygen using the mole ratio from our balanced chemical reaction here, chemical equation. So we're going to have 3 moles of oxygen for every 2 moles KClO3. And then we're going to convert our moles of oxygen into liters of oxygen. Because we're working at STP, we can do 22.4 liters per 1 mole. And it doesn't matter what the identity of the gas is, as long as it's STP. So 0.5 times 3 times 22.4 divided by 2 be 16.8 liters of oxygen. This is actually, this reaction is the one that they use in oxygen candles on nuclear submarines. Well, it's not just nuclear submarines. I think they're all nuclear submarines at this point, but on submarines. So because it generates oxygen and it produces salt as one of the byproducts. So they have, because they have a nuclear generator, essentially a limitless amount of electricity. So they can use that to generate oxygen through electrolysis, but sometimes to just top up their oxygen levels, they burn these candles. And it's like a big salt block, and it sits inside of a special container, and you turn the thing on top and it lights it. And it doesn't burn with like an open flame. It burns with a it smolders. And so it's all red and glowy. And basically as the whole thing gets consumed, you end up with a pile of salt and oxygen. I don't know if they still use it, but they used to use it on space shuttles too, on the space station.
I never thought of that. We somehow need to get more oxygen down.
Yeah, without surfacing. Actually, I think the problem with electrolysis is they have to pull water, ocean water in, purify it first, and then hit it with electricity. You can actually do this at home with a 9-volt battery. If you take water, put it in a glass, add some salt to it, and then just drop a 9-volt battery in it, it will start to produce, I don't remember which terminals which. At one terminal, it produces oxygen. At the other terminal, it produces hydrogen. Don't do that with other electronics. 9-volt battery is not going to shock you. But I mean, you can look at 9-volt battery, right? Okay. Sidebar over. How many grams of aluminum must react with sulfuric acid to produce 1.25 liters of hydrogen gas at STP? Yeah, feels like a lot. This is one of those things though, right? We've built up this stack now. We've got this equation. We know that 22.4 liters at STP is a mole. This is the bridge now from all of this gas law stuff we've been talking about back into stoichiometry. So let's just use what we know, right? We got 1.25 liters of hydrogen gas at STP. For our equation, we're going to need to go 2 moles. So to go to moles, actually, let's write up a solution diagram. So you've got liters of H2. I want to convert that to moles of H2. So once we have moles of H2, we can go to aluminum, because our question here is how many grams of, hey, come back your highlighter. How many grams of aluminum? So we can use moles of hydrogen in this equation to get moles of aluminum. And then for moles of aluminum, we can get grams of aluminum. Okay, so you just start writing these out. I'm going to use this method again. I'll do like a line. So 1.25 liters H2. So how are we going to convert 1.25 liters of H2 into moles? We are sort of using that, but we're starting with liters here instead. The key part of going grams, moles, moles, grams, the Gramwich, is that we need to get 2 moles. So here we're starting with liters, but at STP, what's the volume of 1 mole of gas? Yeah, 22.4 liters is 1 mole. So we can do that because we were told that this is all at, let's use a different color. Come on, STP. So at STP, 22.4 liters is 1 mole. So now we've done this, we've converted from, I'm going to highlight over these as we go through them. So we've done this part. So now we have moles of H2. How do we get moles of aluminum? What's our ratio in our reaction equation here? How many moles of hydrogen for how many moles of aluminum? 3 moles of hydrogen. For how many moles of aluminum? Yeah. Yeah, it is just that simple.
So it would be mole to mole? Is that mole to mole reaction?
Yeah, so that's why we went from hydrogen, liters of hydrogen to moles of hydrogen. So we're going to be converting from 3 moles of H2 to moles of aluminum. So now we've done, let's use a different color. So we've gone from moles of hydrogen to moles of aluminum. You can have these like overlap. All right, so we got moles of hydrogen to moles of aluminum. Now we need to go from moles of aluminum to grams of aluminum. How do we do that? It's on the periodic table.
Oh,
We
the
do
molar
that
mass.
molar mass?
The molar mass. Where's aluminum? Oh, duh, I should know. 26. So we use 26.98. So 26.98 grams of aluminum is 1 mole aluminum. And that does it, right? That solves, we've gone from liters of hydrogen to grams of aluminum. Now all we got to do is the math. 1.25 times 2 times 26.98. So I'm going to multiply straight across the top. And then I'm going to divide by 22.4. Divide by 3, divide by 1. Ooh, he worked this one out ahead of time. So that's going to be 1.00 grams of aluminum. Just almost exactly 1. So a problem like this can seem really intimidating, but this is stuff that you've already learned. The stuff we've already covered. And hopefully you haven't already dumped from your memory. And even if you were struggling with it before, our brains are constantly working on these things sort of in the background. So this has now been sort of like digested and mulled over, because this was, I mean, stoichiometry stuff was like 2 weeks ago, 3 weeks ago or something. So that'd be a good time to go back and review that for these kinds of problems. The key though is that we always need to cross this mole to mole bridge. Whether we're starting with liters, starting with grams, ending with grams, or ending with liters. Because we could have done this if this was aluminum gas for some reason, which is kind of a terrifying thought. We could go from moles of aluminum here to moles of aluminum gas, and we would just use our 22.4 liters again. Okay, now there's actually a few more slides, but that is the end of our time. It's 2 more problems. I mean, I'll stay and view these problems and then post the video later. So if you got to go, Well, you can go. Yeah, yeah. If you got to go, then you can go. And then, I'll post this later. All right, so, volume to volume calculation. So what volume of oxygen will react with 150 liters of hydrogen to form water vapor, which is a gas, at STP? So this is worded really. Oh, and what volume of water vapor will be formed? Really weirdly worded question. Okay, so this is going to be very similar to our last one where we had 150 liters hydrogen. Oh, sorry, actually, I wanted to do another, oops, not that one. Let's do another solution diagram. So you have liters of hydrogen. And then because we're trying to convert from one element to another through our reaction equation, we're always going to go from moles. So we can only go from moles of one element to moles of another element. So we're going to convert to moles of H2. And from there, we can convert to moles of H2O. And then finally, we can convert to liters of H2O. And again, a key here being that we're at STP. We're going to end at STP. So how do we convert 150 liters of hydrogen gas to moles of hydrogen gas?
The number with the 22.0.
22.4, yeah. Yep. 22.4 liters, 1 mole. And I know that we're dividing by liters here because we're starting with liters here. So that way those units cancel. Okay. So now I should write this in here, moles of H2. Now we need the mole to mole ratio. So we have 2 moles of H2, 2 moles of H2O. So now we have moles of H2O. How do we convert from moles of H2O to liters of H2O? It's just a reverse of what we did for, reverse of what we did for hydrogen. Should probably put units in here. Oh. Okay. And that will get us to liters. So we got, oh, well, I see I misread this question a little bit. There are 2 parts to this question. So we're solving this question. The first question was what volume of oxygen will react with this hydrogen? So we can do that next. I'll copy the slide. Uh, 150 times 2 times 22.4. Oh, well, this is going to be. And then we're going to divide by 22.4 and then divide by 2. So it's going to be 150 liters. Yeah. Okay, so that was the first part of that question. Put this in. I'm going to clear page. Okay. So we still have that one we did just now. All right, so that's the water vapor. How much water vapor? And this one is interesting, I think, because we start out with 150 liters of hydrogen and we convert that to moles, but then our mole to mole ratio of hydrogen to water is 2/2, which is the same as 1:1. So when we multiply by 22.4 again, we get exactly the same volume because it's exactly the same number of moles. Nothing changed there. If, oh, maybe this is what he meant by the simpler mole to mole ratios. Okay, so if we have 150 liters of hydrogen, I'm gonna make a prediction right now. We're gonna get our volume of oxygen here is gonna be 75 liters. All right, we're gonna have 75 liters of O2. That's gonna be the answer. And it's gonna be a similar reason to what we just did as to why. So again, we're starting out with our 150 liters of H2. I'll go a little further with that. That's 22.4 liters per 1 mole. And then we have 2 moles of hydrogen for every 1 mole, not H2O. So if we're going to convert back to volume, it's now going to be 22.4 liters H2O to 1 mole. So you can see we're going to divide by 22.4, and then we're going to multiply by 22.4. And so those are going to actually cancel out. This doesn't matter, this doesn't matter. Because so then the only thing that matters is that we have this 1:2 mole ratio of oxygen to hydrogen. And since the volume is only dependent on the number of moles, we just take 150. Well, I'll type it in with the 22.4, but 150 times 22.4 divided by 22.4 divided by 2, 75 liters O2. So this is only going to work though when you're going from, well, not just liters, but volume. So volume of something, it's a volume to volume conversion. You can use the simple mole ratio and just divide 150 by 2 to get the amount of oxygen. Or you can set up this whole thing. Probably not advisable on a test when you have a limited amount of time, but. All right. One more question. Magnesium metal reacts with HCl to produce hydrogen gas. How many grams of magnesium are needed to prepare 5 liters of H2 at 735 millimeters of mercury and 18 degrees C? All right. He's gone and done it. We're no longer at STP. Making everything more complicated. But this is good. This is good. I mean, there's a reason it's here, right? So we have, you always got to start with what you're given. So we're going to have 5 liters of hydrogen at these conditions. So we can calculate our number of moles. Oh wait, is there a class in here after this? Oh, I think there is. There class in here? Yeah. What time is it? Okay. We'll be done soon. Thanks. Let's start at 10, so we're okay. All right. So we're gonna start with what we're given, but for reaction equations, again, we have to be in moles. So we have to know the moles of hydrogen in order to use it in this to figure out how much magnesium. So what's our reaction diagram here going to be? Our solution diagram is going to be we have liters. We're going to convert that to moles. This conversion from liters of hydrogen to moles of hydrogen is not going to be quite so simple. We're going to have to use, well, let me ask you, what do you think we're going to use? So we have a volume, we have pressure, we have a temperature. We want to know N. I might not have time for this question. So with all of these things, this is where I would have like a list of all these equations written out. We can use PV equals nRT. The caveat is that we need R, we need to convert this to atmospheres to use our R value. So that's 760 millimeters of mercury is 1 atmosphere. We're also going to add 273.15 to this to convert it to Kelvin. It's going to be 295.15. 760. It's going to be 0.967. So then we're going to have our pressure of 0.967 times our volume of 5 liters divided by 0.08201 times 291.15. I can zoom this. That's going to equal our moles. So it's going to be 0.202 moles hydrogen. So now we have, so this, everything up here was to do this conversion. So now we have 0.202 moles of H2. You can set up the rest of the stoichiometry. We want magnesium metal, or how much magnesium. So we have a 1-to-1, thankfully. So 1 mole H2, 1 mole magnesium. God, I gotta figure out what's going on with this Apple Pencil. 24.3. Yeah, grams of magnesium per 1 mole magnesium. So 0.202, we have a 1-to-1 mole ratio times 24.3, going to be 4.91 grams magnesium. So the hard part there being that we have to do this, all of this math in this top right corner first to get moles of hydrogen, because not at STP. All right. And then skip anything about partial pressures. Wish this told me when those messages were sent. I'm sorry, but I have to hop off because somebody else is going to be taking over the room. So thank you to those of you who tuned in on Zoom. I'll post this recording later, and if you want to message me about any questions that you might have had, please feel free to text me or message me on Canvas. Stop the recording.